Okay, so welcome to week 3. So this is another preview of coming attractions. I'm going to do a very brief hand-wavy look at doing simulation as yet another way of computing option prices. Professor Lahosky's course in the spring is obviously going to get vastly deeper into this than I will even pretend to get close to. And it is one of the most important mechanisms for pricing options that you're going to see. Okay, so let's suppose that we have a coin and we want to know what the probability is that we're going to get heads when we flip this coin. We don't really know at this point whether the coin is fair. Maybe it's a weighted coin so that it's much more likely to get heads or tails. Maybe it's a phony coin and only has 2 heads on it. So what do we do to figure out what the probability is of getting heads when we flip this coin? Well, according to the law of large numbers, if we have a large number of samples of random variables that are independent and identically distributed, taken from some probability distribution with mean mu and variance sigma squared, then if we compute the mean, then that mean can be an estimate of the actual mean. And in fact, as the size of the sample goes to infinity, this mean, according to the law of large numbers, gets closer and closer to the actual mean. So we're not sure about our coin. That means that we're going to need to flip our coin a whole bunch of times to get an estimate of what the actual probability of heads is. Now that raises an immediate question, which is, what is a whole bunch of times? We'd like to have some way of measuring how confident we can be that xn bar is getting close to their actual mean. Here, we can make use of the central limit theorem that says, as the sample size goes to infinity, the distribution of the means of our samples is going to converge to a normal distribution, with the mean being the actual mean for the random variable x, and the variance being the variance of x over n. Now, the important thing here is that the central limit theorem applies regardless of what the underlying distribution of this random variable x looks like. Whether x is normal or uniform or exponential or some other kind of distribution, the so-called sampling distribution of the means is going to converge to normal around the actual mean with variance of the variance of x over n. So the bigger we make n, the more confident we will be that xn bar is close to the true mean. Now, if we already know the true mean and the variance for the random variable x, then we know from the normal distribution properties how to find n to give us some desired level of confidence. But in fact, it's more common that we don't know the actual mean and the actual variance of our random variable in advance. All right, so we can use xn bar as an estimate of the true mean, and we can use the standard deviation as an estimate of the square root of the variance. The sample standard deviation divided by the square root of n gives us the so-called standard error of the mean. That is, the standard deviation of the mean of x, not the standard deviation of x itself. All right, so then a 95% confidence interval for the actual mean, based on our knowledge of the normal distribution, is a sample mean minus 1.96 times the standard error to the sample mean plus 1.96 times the standard error. That is, under the central limit theorem, if n is large, the probability is 0.95 that the true mean of the random variable x is found in this interval from the mean of the sample minus 1.96 times the standard error to the mean of the sample plus 1.96 times the standard error. Now, because n is in the denominator here, as we increase n, that narrows our confidence interval. So if the random variable represents the price of some financial instrument, then we can increase n until our 95% confidence interval gets down to a penny or down to a tenth of a cent or whatever precision we need. As an illustration, let's suppose that we have a random variable with known distribution, normal 0, 1, that is, it's a standard normal. Its mean is 0, its standard deviation is 1, and we draw a random sample. We would like to know how big that sample has to be in order for our 95% confidence interval to fall within a quite narrow range, between plus or minus 0.001. All right, well, that means that we need n such that 1.96 times our standard error, that is our estimate of sigma divided by the square root of n, equals 0.001. Now we know that the true sigma is 1, and we're just going to approximate 1.96 as 2. So if we rearrange the terms in that equation, this tells us that n is approximately 2 over 0.001 squared, and unfortunately that works out to 4 million. So it turns out that we have to draw 4 million samples from the standard normal distribution in order to get a 95% confidence interval of plus or minus 0.001 for our sample mean. Here's how that looks in actual code, and in fact let me pull up my code file. Okay, so this code file is called norm01 confidence interval test. We're going to use NumPy for this rather than a list of floats because NumPy will let us do vectorized computations, which is vastly faster than looping through items in a list. Okay, so what in the world is this program doing? Well, we have determined that we need to have a sample size of 4 million in order to have a 95% confidence interval within plus or minus 0.001. And what I'm doing here is drawing 1,000 samples of 4 million values from the standard normal to see whether, in fact, roughly 95% of those samples result in confidence intervals containing the true mean of 0. Okay, so 1,000 times we're going to generate a random sample of 4 million values. So N01 sample is 4 million samples drawn from our standard normal distribution. We're then going to compute the mean of that sample. That gives us xn bar. And we can compute the standard error, which is the standard deviation of our sample divided by the square root of n. Now, 95% of the time, according to the central limit theorem, the true mean of 0 ought to fall within this confidence interval from xn bar minus 1.96 times the standard error to xn bar plus 1.96 times the standard error. So if the true mean is within that confidence interval for this particular sample, then we're going to increase the count of times that we are in the confidence interval. We're doing this 1,000 times. Now, 1,000 is arbitrary, and I should be clear that we're not proving anything here. We're just testing things. And the idea here is that the number of times that we do have a confidence interval containing the true mean divided by our 1,000 samples ought to be approximately 0.95. Okay, so if I run this, actually this runs for quite a long time. I'm drawing 4 million samples from a standard normal, and I'm doing that 1,000 times. So I've got 4 billion draws from standard normal going on here. All right, I'm going to kill this off, in fact, and show you the actual output that I got from running this thing several times here on slide 9. And you can see in these half dozen test runs that I did that more or less 95% of the time, our confidence interval computed using the sample mean and the sample standard error did in fact contain the true mean. Okay. Now, I said this before, but I want to repeat that the central limit theorem applies regardless of what the underlying distribution looks like for the random variable that we're sampling. The central limit theorem has to do with the distribution of the means of samples, not of the underlying distribution of the random variable from which these samples are being drawn. So as another example, let's suppose that we have a known uniform distribution from which we're drawing values between 0 and 1. Well, the mean of a uniform distribution is just the midpoint, so the mean is going to be 0.5. And it turns out that the variance here is 1/12. So the square root of the variance is close to 0.2887. Well, the central limit theorem still applies, so we can figure out an n for the uniform distribution that will give us this narrow width on our confidence interval, plus or minus 0.001. Doing basically the same calculation we did before, we discover in this case that our sample size n should be about 335,000 draws from the uniform distribution. And here on slide 12 is code that's very similar to what we saw before, with just minor modifications. We're drawing 335,000 samples from a uniform distribution. Now, rand(n) is a standard normal distribution. Rand in the np.random module is a uniform distribution on 0, 1. And the true mean for the uniform distribution is 0.5 rather than 0. So once again, we're doing 1,000 samples of 335,000 draws from a uniform distribution, and we're testing to see what fraction of that 1,000 times our computed confidence interval contains the true mean. And here on slide 13, I have the results of running that particular test half a dozen times. And once again, you can see that the fraction of time that our computed confidence interval contains the true mean of 0.5 is about 95%. All right, well, what in the world does all this have to do with finance? Well, according to the Black-Scholes-Merton model, the evolution of a stock price follows a so-called geometric Brownian motion. That is, a small relative change in the stock price is driven by a hopefully upward drift based on the current risk-free interest rate and a stochastic volatility part where sigma here is the standard deviation of return on the stock, and WT is something called a Brownian motion or a Wiener process. Wiener for Norbert Wiener, not for the hot dog. Okay, so the characteristic of a Wiener process is that it's a random variable with a distribution that is normal with mean 0 and variance t. That means for simulation purposes, we can rewrite the Wiener process using a standard normal variable little z by saying that the Wiener process up to a time little t is equivalent to the square root of that time times z. All right, now it turns out that the solution to this equation on slide 14, which you will learn all about in stochastic calculus, is that the stock price at some final time t is equal to the stock price at the initial time 0 times e to a deterministic term plus a stochastic term. Now we know how to get a sample of standard normal random variables, so we can simulate a large number of values for S sub capital T, and therefore, because we know the payoff for European call at time capital T, we can use simulation to get the mean and standard error of a large number of simulations of call values. The call value is simply the discounted expected value of the payoff of the call at the expiration time. And so here we have our discount factor right here, e to the minus rt, with our payoff function, that is the ith sample of the final stock price minus k, or 0, whichever is greater. Here on slide 17 and following on slide 18, I have the setup for a European call with the same parameters that we've seen before with the Black-Scholes-Merton model and the binomial tree. And then on slide 18, I have the actual simulation code. So our stock price initially is $50. Our strike is also $50. Our risk-free rate is 10%. Our volatility is 40%, and our time is 5 months. We have not this time determined in advance what n should be. We're just going to go ahead and choose n to be 100,000, and then we can see whether that gives us a standard error that we like. If not, we can increase n and run the test again. All right, so in the simulation, step 1 is to draw a sample of standard normals, which will be our z sub I. So once again, we're using rand n to get n standard normal draws. Then for each of these samples, we need to compute s sub I, that is the stock price at time t, for each of the z sub i's, each of the sample standard normal draws. Fortunately for us, we can use the vectorized e to the x function in NumPy to do this for all of the s sub I at once, rather than having to do this in a loop. So if you compare our code for s sub I on slide 18 with the formula on slide 16, you'll see that we're computing the correct thing. Once we have the s sub I computed, we want to get the discounted payoffs of all of those s sub I. And here we have to be careful to use the vectorized maximum function that will return a vector of I values rather than the max function, which would just return a single maximum value. All right, so the NumPy maximum function is going to compute for each I the maximum of s sub I minus k and 0. We'll discount those back, and that will give us our vector of c sub I, our vector of simulated call prices. Finally, the mean of that vector of call prices gives us the call price computed by simulation. And you'll notice that we're missing a rather important step here, which is to determine the standard error and the confidence interval for how good this call price is. All right, here on slide 19, I've run our call price calculator half a dozen times, and we get prices that are within the vicinity of 6.12, which is what we got from the Black-Scholes formula. Based on casual inspection, it looks like these call prices are not really as close as we would like. We would like them all to be within about 1/10 of a penny of $6.12. Okay, so that is our brief introduction to using simulation for option pricing, in this case for pricing a European call.